Okay, good morning. So today we will continue our discussion from last time about the friction in the fluid flow. And now we will discuss about friction that is caused by pipe accessories, or we usually call it as fitting. So fitting or pipe accessories, basically all the device or the equipment that we put uh, in between of a piping system. So the example is valve. You know the valve, right? It's used to adjust the flow velocity, or sometimes you put enlargement or contraction when you want to connect two pipes with different diameters. Or sometimes you put, you call it T or Y. It's because of the shape is like a T shape or Y shape. So it's this type of fitting is used to divide the flow. For example, from one pipe, you want to divide it into two different pipe, maybe the same diameters or different diameters, then you put T or Y. So this is the example of fitting. This is the T, this is the Y, and this is the elbow. Elbow is to change the flow direction, because in the plant or in the chemical industries, you will need a very complex pipe arrangement. It cannot be just in one line only or one direction only. So you need to change the direction of the piping. It means you need to change the direction of the fluid in order to fulfill the requirement. Elbow itself, you will have 45-degree elbow or maybe 90-degree elbow. This is the diffuser, and this is the sudden contraction. Okay, the other types of fittings is called a strainer. What is the function? Do you know the function of strainer?
It has something to do with the flow pattern, sir.
This is just showing the flow pattern. Strainer, actually it's a filter. So if in some pipelines we are afraid that maybe some solid particles will be flowing together with the liquid or with the gas. So in certain parts of the pipe segment, we install a strainer. So inside this one is a filter. So in the outer part looks like this, the inner part looks like this. Then during the flow, if there is some solid particle flowing together with the gas or with the liquid, in the filter part, the solid will be retained. So the flow pattern will be changing inside the strainer. So basically, it's not directly like this, right? If you see from outside, so basically it's flowing downward first, and then the solid will be remaining in the filter, and then the liquid or the gas will continue to flow. Or maybe the shape of the strainer is just like this. So inside, there will be some filter put inside the pipeline. Okay. The other type is valve. So the valve, we have different types of valve, but basically the function of the valve is to control the flow rate, either to just open and stop the flow, or maybe you can adjust the flow rate. For example, like this one, we call it gate valve because its function as the gate. So when you usually in gate valve, it's just to open and uh, close. You may use the gate valve to adjust the flow rate, but it will be not sensitive in changing the flow rate, because the opening is like gate, like whether it's open or it's closed. Okay, the other types is plug valve. you can use the inner part of the plug valve is like this. So you can plug valve is a bit similar with the gate valve. So it's to open. So if it's open, that it means the liquid will be flowing freely inside the pipe. But if you close, then you stop the liquid flow. But it can be used to, the main function is to open and close, but you can use to adjust the flow rate. It's more sensitive compared to the gate valve or globe valve. Globe valve uh, have inner part looks like this. So you have this in this part. So when you open the what you call it, the handle, the wheel, yeah. When you open the when you turn the wheel, then this part will it can move up and down, and you can adjust how much by adjusting the wheel, you can adjust how much the disc will move up or move down. So when the disc is surely moved down, then it will be the valve will be closed. If it's moved up, then some space inside this chamber, so the liquid or the gas can flow. When it's all moved up, then it's 100% open. Okay, like this. Okay, same with group valve, but slightly different direction is called angle valve. So angle valve, the difference between the angle valve and group valve is the group valve is normally the doesn't change the direction of the fluid, but in angle valve, uh, for example like this, then the fluid can move from here to here or vice versa. And the opening will be adjusted by the wheel, so it will move up and down like the curve valve. Okay, the other types is butterfly valve. So butterfly valve can be used to adjust the flow rate, but the opening is slightly different with other types of valve. It will be like this. So in this position, there will be no flow. But when it's slightly moved, like this one, or maybe can move this one, then there will be more flow inside the pipeline.
Sir, question, sir.
Yep.
What's the difference between the butterfly valve and the gate valve, sir?
The but oh, the gate move for this one, it moves like up and down.
Oh, okay, okay, okay. Okay, I
And
understand, sir.
okay, but this one is move like yeah, this one like this one.
Okay, okay, sir, I understand, sir.
Yeah.
Thank you.
And it can be used to adjust the flow rate. The gate valve can, but normally it's not for adjusting the flow rate. Okay, the most common one that you might be using at home is called the ball valve. The ball valve, why it's called ball valve? Because the inner part looks like a ball. So you have a ball shape, but in one part, the ball is has hollow inside the body. So by changing the position of the ball, then you can change how much the fluid can flow into the valve and into the pipeline. Okay, the specific types of valve, we call it check valve. There is two types of check valve. The one that move uh, vertically, like this one. This one calls lift check valve. because it moves up and down. This one is called swing check valve. It moves right and left. But the function is the same. For example, this one, the valve uh, is designed to flow the, for example, liquid from this one direction to this one direction. So when there is liquid flowing this one, it will move the check valve. The flow can cause the valve to move upward, so the liquid can move to the right side. Same for this one. It's designed to move from here to here because the pressure or the velocity of the liquid can cause this part to lift. However, if the liquid or the gas flowing in the different direction, for example, this one, or in uh, lift check valve, they flow like this one, the in lift check valve, the valve will move downward. Or in this one, the valve will move to the left side. What happened? So the liquid or the gas cannot flow inside the pipe. So the function of check valve is basically to prevent what we call backflow. Backflow is caused by back pressure. So for example, in a certain of the pipe, we want uh, the fluid to flowing only in certain direction only. Yeah, we but you like for this one, right? So for normal condition, the flowing is to the right side because the pressure in point one is higher than point two. But sometimes when there are some problems with the process, for example, so pressure at point two will have higher pressure than pressure at point one because maybe malfunction of the reactor or malfunction of the release valve or something like that. So the pressure at point two will be higher. So there will be backflow. If we do not want backflow to happen, then install the check valve. Because sometimes it's dangerous for the process if there is backflow or back pressure. Okay, any question until this one? You can see from maybe from YouTube or other source how each of these valve, the animation. I think there's several videos that you can watch in YouTube. But basically, by installing fitting, installing the valve, elbow, sudden enlargement, diffuser, etc., it will be causing the change of flow pattern, right? So if without fitting, the flow of the fluid is smooth inside the pipe. When flowing through the fitting, the fluid will experience slight change or maybe sudden change in flow pattern. So this flow pattern, the change in flow pattern will cause some energy loss. So the same concept is applied as EF. You still remember EF, right? EF is this the unit will be joule per kilograms. This EF is actually the energy that lost to the environment caused by
Friction,
the,
sir.
the friction between the fluid and the inner part of the pipe wall. So there will be some energy that lost to the environment, then we quantify it by EF. The same as well as in the fitting. When liquid or gas or fluid, generally fluid flowing into the fitting, there will be some loss of energy. When the fluid passing through the fitting, the loss of energy to the environment is similar to the, the concept is similar with the EF. What will be the effect of energy loss?
Less pressure by the fluid, sir.
Yes, the fluid will experience pressure drops or pressure loss. Same with fitting. Due to uh, the fluid flowing into the flowing through the fitting, there will be some pressure drop due to the energy loss. Then how to quantify the energy loss? Basically, similar with calculation of EF. So first, the friction loss by fitting can be quantified by knowing the equivalent length or panjang equivalent. Equivalent length means the fitting will have the same pressure drops, same as straight pipe. For example, if you have a valve with the diameter of 3 inches and length of valve, right? Length of valve is, for example, just maybe 10 centimeters. It will create pressure drop same as straight pipe with diameters 3 inches but length 25 centimeters. So this valve, say they have equivalent length 25 centimeters. Okay, can be understood, right? So the equivalent length of fitting is not the length of the fitting, but it is the length of the straight pipe that causing the same pressure drop as the fitting. That's the concept of equivalent length.
So there aren't any more complicated formulas that we have to remember, kan, sir? Only one.
Sorry again, sorry.
We only have to memorize one formula, right, sir?
Yes. So if the fitting, if you know the value of equivalent length is known from the data. So from experiment. So you can get the equivalent length of certain fittings from the data. If the value of the equivalent length of the fitting is known, then to calculate EF, this is EF, right? EF, then you just use the same formula as calculation of EF of straight pipe. Okay, what does it mean? So it means you need to know or to calculate the linear velocity first. After you need to know the velocity, then you also need to know the diameters. You need to calculate the Reynolds number, right? After you calculate the Reynolds number, you calculate the friction factor, whether it's laminar or turbulent, then you decide how to calculate the friction factor. After you have the value, then you can use this equation. This equation is used if you know the equivalent length.
Sir, question, sir.
Yep.
In the formula of the frictional energy there, why is there 2u², sir?
Sorry. Two.
Why is there 2u²,
Oh,
sir?
okay. Okay. Again, there is some only until this one. The formula is only EF is 4 FF L over D half to square, right? So you just use the same equation as the calculation of EF of the straight pipe. It means you need to calculate the friction factor first. Okay. The other method to calculate the friction loss by fitting, if you know the fitting constant. Okay, if you know this one need to change also. Sorry for the typo. If you know the value of the fitting constant, where you get the fitting constant, again, it's from the data. The data comes from the experiment done by somebody else. So basically, fitting constant is calculated by variate the velocity. So you install the fitting and then you variate the velocity entering the fitting, and then you calculate the pressure drop before and after fitting. Then you will have the value of the constant. So if you have the value of the constant, you can just use this equation to calculate EF. Later,
Sir, I have
yep,
a question, sir. It says friction loss due to kinetic energy, right, sir? Is that constant? A constant of amount of kinetic energy being lost, sir? Is
it
that right?
means the ratio between the EF and the kinetic energy is always constant. That's the definition. This is the kinetic energy, right? This is the EF. In terms of specific energy, all the unit will be joule over kilogram, right?
Yeah, yeah, okay, sir.
So when you increase the kinetic energy, you increase the velocity, the increase in EF will be linear.
Okay, sir, I understand, sir.
Okay, that's why we call it friction loss due to kinetic energy loss, because it's linear and it will be quantified as fitting constant. Yang ini tolong diganti ya persamaannya, yang di atas KL. So the nominator will be KL. So by the definition, because EF is 4 FF LED, this one, so KL will be this one, or equivalent length will be this one. Any question until this part? Okay, then I'll continue. This is the example of the value of KL. You can see this is the elbow. All are elbow, but have different value of KL. What will be the difference? The difference is the arrangement of the elbow. This one is for the regular elbow. This one is long radius, 90°. This one is long radius, but only 45°. And this one is regular 45. Regulars mean small. Long radius means very long, big radius. And what is the plate and threaded here? Do you understand the differences?
I don't understand, sir.
This is how you connect the elbow to the pipe. Flat is, do you know the meaning of flat or the translation of flat?
No, sir.
The others, ada yang tahu artinya flat apa? Or threaded? Flat means you connect the elbow by using alat las. Apa sih bahasa Inggrisnya? I don't know the term in English. You know when you want to connect steel to steel, or maybe yeah, steels, when you want to connect, then you can use alat las. Ada yang tahu bahasa Inggrisnya? Let me check.
Is it welder, sir?
Yes, welding device. Yeah. So you weld the, I think, plate. Let me check. Kok terjemahannya dikuliti ya? Oke, oke, oke. Okay, I think it's correct. The flat is when you connect the the elbow to the pipe by welding. But threaded if you want to connect by screwing the elbow. So the pipe or the elbow part, they have the ulir, the screw part. So you thread it. It will be different in flow pattern. That's why its connection, its fitting have different value of fitting constant. Or if you check the valve, you have globe valve 100%, angle valve 100%, gate valve 100%. It means fully open. Different valve, although it's fully open, it will have different value of fitting. And also when the valve, same gate valve, but like a quarter close, half close, it also have different value of fitting. Again, it's because the fluid will experience different flow pattern inside the fitting. Higher KL means what? If the fitting have higher constants compared to the other, it means that fitting will cause
Kinetic energy to be less and the frictional energy to be greater.
yes. Basically, when the KL of the fitting is higher, then EF is higher for the same velocity. Because from this equation, right? Higher EF means the pressure drop will be higher. Same concept with the equivalent length. If the fitting have higher equivalent length, then it will cause higher EF or higher pressure drop. Okay? Any question until this part?
Sir, I have a question, sir.
Yes?
If the pipe is threaded, sir, won't it leak, sir, if you just put the screw on the pipe?
Good question. But yeah, but you need to put something in between, right? For example, if you screw the valve to the pipe, or when you screw the 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 cran, the valve uh, to the wall, then you need to add some thing, right? Like the white, I don't
The
know,
white tape, right, sir?
white, either it's white tape or it's pipe glue.
Oh, okay.
There's some specific glue that you put on the thread, then you put the the valve or the fitting, to secure the fitting and to seal the space between the pipe and the fitting.
Okay, thank you, sir.
Okay. Okay, then this one is just basically to see why the fitting can cause the EF. So this is the analysis of Bernoulli equation by assuming same height, right? So the equation is comes from this one. If you install sudden enlargement, you will have a higher diameter in the outlet, less velocity, and higher pressure. So by putting the Bernoulli equation, because the position remains the same, the potential energy is the same, the delta is 0, Z1 equals Z2, then EF is only from change in pressure and change in the velocity. So from the mass flow rate, this one, please check again our previous slide. You can correlate the velocity, inlet and outlet, as the function of the ratio of diameters. For example, you express as velocity at inlet, then you can change the first equation into the second equation. Okay, then basically it's just the manipulation of the equation. You introduce the constant called Cp as the delta P divided by this one. So you can put Cp here. And this one, you call it the constant. Same, right? So the equation can be changed into this equation. So from this derivation, basically you do not need to memorize the equation. The exam is open book anyway. So basically by seeing the derivation of the equation, you may see that actually for sudden enlargement, the constant will be depending on the ratio of the diameters. Because there will be a different size of sudden enlargement, right? It will be depending on how big is the diameter in the inlet and the outlet. So the ratio will cause the differences in KL, the fitting constant of the sudden enlargement. That's why for sudden enlargement, the fitting constant will be function of this one, d1 by d2 to the power of 4. And the table you can get from the textbook. Then the AR is the ratio. AR is the ratio of the area. So the area between the smaller and bigger diameters, inlet and outlet diameters, then you can have the value of KL. So for example, if you need to calculate the EF from sudden enlargement, if you want to calculate EF of sudden enlargement, then you need to calculate first AR. AR means this one. Okay. Cukup jelas ya? Clear enough? Okay. Now,
Okay.
you already understand that straight pipe will have EF. Fitting will also have EF, right? So when you have very long very long pipe segment, for example, you have one segment of pipe, the first segment is consists of N1 of straight pipe. with the diameter, this is the same diameter, D1. And then in this segment, so in the first segment, segment 1, the diameter is the same. The diameter of the pipe is the same, but in between of the pipes in this segment, you put fittings. For example, valves, elbow, etc. in between of the segment. Then to calculate the total EF, will actually, you need to calculate the EF from each pipe and each fitting.
Sir,
Yep.
since there is only two different diameters of pipes, it means the fitting there's only one fitting, right? In this case.
No, for example, we have two segments. Each segment consists of several pipes and several fittings, but each segment have different diameters. Like for the segment 1 is D1, and then segment 2 is diameter 2. D1 will be different with D2, but in the same segment, all have same diameters. So you need to calculate first EF of each segment. EF of each segment will be total of EF of each pipe and each fitting. Same for the second segment. So it will be the sum of all the EF. Okay,
Okay, sir.
you can see, right? This one is using, so this one is for the pipe. This one is for the fitting. But if the fitting, the data that you have is equivalent length, then you can use the first equation. Okay, do the same for the second segment. Okay, in the first segments, you are using the velocity at the diameter 1. For the second segment, you use the velocity of the second diameters. But if you want to connect these two segments with different diameters, you need one more fitting, right?
Yes, sir.
Either is sudden enlargement, sudden contraction, diffuser, or reducer. So you need to calculate the friction EF for the fitting that connected from D1 to D2. Don't forget. So this is the EF of connecting fitting. Which velocity that you use to calculate the EF? You use the velocity of the inlet of the connecting fitting. So it's D1. So if you connect the D1 to D2 using fitting, then the calculation of EF of the connecting fitting will be using the velocity of the inlet velocity. So at the basis is the inlet. Then you have this one, this one, this one, right? This one, and this one. Then you take the total. This is the total EF from segment 1, segment 2, and connecting fitting. Okay, well, we need to calculate the total, so you can put into the Bernoulli equation. If you analyze the Bernoulli equation from the inlet, inlet means before entering segment 1, and outlet means after coming out from segment 2. Yeah, so point 1 is inlet of segment 1. Point 2 is outlet of segment 2. So you can use Bernoulli equation by putting EF, but EF is this one, the total EF from both segment and the connecting fitting. Okay, any question?
So far, it's okay, sir.
Okay. So as the conclusion, just make the total EF first, and then use the total EF for the Bernoulli equation. Okay. Now, how about the complex? Okay, there will be several typo, so I will correct it later. How about the complex piping system? Complex means sometimes the pipe is divided into certain more pipelines. So basically, for complex piping system, you just remember the principle of continuity equation. The conservation of mass. The total mass will be remain, the total mass flow rate will be remaining the same. So if you have one pipe divided into two pipes, then the total mass flow rate in the two pipes should be the same as the mass flow rate in the first pipe, right? Like this one. This is 2, this is 3. So M1 should be M2 plus M3. Or in this part, if you analyze from point 4 is here, point 2 is here, and point 3 is here. So the mass flow rate at point 4 will be the sum of mass flow rate at point 2 and point 3. Okay, if the density is constant, the volume, this is kilogram per second. The unit will be mass over time. For the same density, constant density, then the flow rate will be the same. Okay, and the energy balance is Bernoulli, right? Energy balance equation, if you have pipe segment I with the diameter of the I, same diameters, and length of I, so the total energy from one point to the other point will be the same, right? If the pipe have constant diameters, what will be the effect? If you have a constant flow rate, and D is also constant,
The mass flow rate of 4 will be half of 3 and 2, sir. Is that right?
oh yeah, oh no, I mean, if you have one pipe, and then the length is E, and then the E, so what will be the same? The velocity, right?
Yes.
If you have the
Yes, sir.
constant flow rate and then the constant diameters, then the velocity will be the same. So if you analyze the any point, for example, this one, with the constant velocity, then we will have this equation. The position will be different, right? Of course, it's a straight pipeline, but maybe different position. So this is the Bernoulli equation with EF is this one, and linear velocity is this one. EF is joule over kilogram. Linear velocity is meter per second. So just remember this principle. How complex is the system? First, you need to apply the conservation of mass. The mass flow rate will be the same. Then If the fluid is incompressible, the density is constant, then the volumetric flow rate is constant. If the pipe diameter is constant, then the linear velocity is constant. Then you just need to use it in the Bernoulli equation. Okay, for example, it's like this one. The pipe is coming from point E inlet to the point O outlet. The number is, I don't know why in the number is 1, 2, 3, 4, and 8. Okay, so as the mass conservation applied, the mass flow rate through all the segments will be the same. Okay, the next principle will be the total pressure drop from inlet point I to outlet point O. The total pressure drop will be this one, right? This one, E. Pi minus Po will be the total pressure drop of each segment. The sum of pressure drop of each segment. This one. So this will be Pi minus Pa, Pa plus Pa minus Pc plus Pc minus Pd plus Pd minus Pb. Ada yang kurang ya? Plus Pb minus Po. Yeah, this is the total of the pressure drop. You need to calculate the total pressure drop. Sorry, you need to calculate the pressure drop of each segment, and then you sum the pressure drop. How to calculate the pressure drop from each segment?
Bernoulli, sir.
Yes, it's from the Bernoulli. You need to check first the condition of the pressure, the velocity, the height, and then you need also to calculate the friction energy, EF. Okay. Or maybe the arrangement is like this. From the point 1, point inlet to outlet, in point A, the flow is divided into direction, into pathways. Goes to the C, D, and B, and one is goes to the E, F, and B. Okay.
Sir, for the mass balance,
Yep.
M2 equals to M3 plus M4 or M3 equals to M4, sir?
M2 equals M. Okay, from the mass balance, let's see. M1 will be equals
M2 plus M5.
M2 plus M5, correct.
Yes.
And then M2 will be equals M3 will be equals M4.
Yeah, there's a typo there, sir.
Okay,
M2.
okay. Let me check later. And M5 will be equals M6 and equals M7. Yeah, there's a lot of typo in this slide. This one, right?
Yes, sir.
Okay. Then how about the pressure drop? The pressure drop should be the same from each of the line. It means the pressure drop of A and B should be the same whether it's calculated from the top line or it's calculated from the bottom line. Or PA minus PC plus PC minus PD plus PD minus PB, this one should be this one. Same. A minus E, E minus F, F minus B. Or it will be the same as PA minus PB. Why it should be the same? Why this one should be the same?
Maybe because the mass flow rate of 2 and 5 is the same, sir.
2 and 5.
But I don't know, sir.
Mass flow rate at point 2 should not necessarily have to be the same at point 5. But the pressure drop at the top line should be the same as the pressure drop at the bottom line. The total, right? From A until B from the above and from A until B from the below line. Why? What will happen if the pressure drop is different?
Backflow, sir?
Backflow, correct. So the fluid will not flowing to the outline. Okay. So how about if this one is higher, for example? If the pressure drop of the top line is higher than the pressure drop of the bottom line, what will happen? The fluid will be flowing to the top or to the bottom?
It will go down, sir.
Are you sure?
Oh, wait.
To the top, sir?
Why?
Because the pressure drop is greater.
Yes. If the pressure drop of the top line is higher, it means at point B from the top, the pressure will be lower than point B from the bottom, right?
Oh, yeah, I understand, sir. I understand.
So it means if the pressure drop is higher at the top, the point B from the top, the pressure will be lower than the pressure from the bottom. So the flow will be backflow to the top line. Okay, I need to make some correction again. This one Pi minus Po, P1 minus Pi minus PA, PA minus PB, then plus PB minus PO. Okay, any question? Wait. Okay.
So far, it's okay, sir.
Okay, so now we need to check this example. So you have a pipe arrangement from point A in segment 1 to point B, and then from point B, the flow is divided into segment 2 and segment 3. Segment 3 goes to point C, and segment 2 goes to point D. Both in point C and point D is open to air. So it means PC will be same as PD will be, okay, let's assume it 180 amp. Okay, the condition of each pipe you can see from the table. So for pipe 1, the diameter is 3 inches, the length is 120 feet, and so on. Pipe 2 and pipe 3, the data is in the table. And then the differences of height of the elevation, you can see from this table. Okay, then the water flows from point A in pipe segment 1 with the volumetric flow rate 140 liter per minute. Okay, now how can you calculate first how much is flow rate at segment 2, this one P1, right? And P3. And also how much the pressure at point B. Okay, don't see the solution because the solution is a bit confusing. And I don't know whether it's right or wrong because I'm not the one that making the solution. Okay, how can you calculate the velocity at segment 2 and segment 3? By using what kind of equation?
We can use the mass balancer.
Yes, you can use the mass balance. So P1, I'm using directly the volumetric balance, right? Assuming the density is constant. So should be M1 equals M2 plus M3, right?
Yes, sir.
But when the density is constant, you can just use the volumetric conservation. Then after this one, seeing the data,
You can change it to velocity and area.
do you need? You already have the value of this one. And you have this equation and you have this data.
Should you count the pressure drop, sir?
No need.
No need, right?
Just see this one. You already have the value of volumetric flow rate at pipe segment 1. You know the formula of mass balance equation. You have the data of the pipe. Please pay attention carefully. How much is P2 and P3? Are you?
Masih rada pusing, sir.
Okay, but you all understand, right, that the volumetric flow rate at point 1, the segment one is pipe, this one, will be the total of the volumetric flow rate at pipe 3 plus, pipe 2 plus volumetric flow rate at pipe 3. Can you see the data of the diameter of pipe 2 and pipe 3?
It's the same, sir. Oh my God.
So it's the same. It means
It means it's half.
half, correct. So P2 will be equals P3 will be half P1. It's simple because the diameter is the same. But how if the diameter is not the same?
Harus di ratio ya, sir.
Yes, then you need to take the ratio of the diameters of each pipe. Okay, then how to calculate PB? Pressure at point B.
Oh, we can use Bernoulli because ada elevation kan, sir, in
Yes.
terms of feet.
So you can make the Bernoulli from point A to point B. PA density plus PZA plus 2A square will be PB over rho PZB plus half UB plus EF. Correct? Don't forget EF
Yes, sir.
because you already know the concept of friction.
Sir, the velocity at A and B, would it be the same, sir?
Yeah, that's my next question. What is the value of OA and what is the value of UB?
Since it's not branched yet, so I guess it should be the same.
Yes, correct. So you can use basically what will happen in point B that you need to install the fitting, right? The
Yes,
fitting is
sir.
the branch. But if you just comparing at point A and point B, it's just before the line is branched. So you can assume or you can say that the velocity at point A will be the same as velocity at point B. Then it can cancel out, right? Then you have the position of B relative to A, then you just put the value. Don't forget, change this one into velocity. Okay, any question?
So far, it's okay, sir.
Okay, yang lain ada pertanyaan from others? If no, then I'll continue to, so no need to check the solution is a bit confusing because actually the soal is very simple. Okay, now we will see about the friction for non-circular pipes. Non-circular pipes mean the pipes that have area is not circle or pipe with circle area but not fully filled with the fluid. This is the case if you are flowing liquid. So sometimes the liquid is not fully filling the pipe cross area. So you need to calculate first, remember, the equivalent diameters. Equivalent diameters is the cross-section area. Which cross-section area? If the picture is like this.
Of the liquid, sir.
Yeah, this is the liquid area divided by the weighted perimeters. So for this case, the Reynolds number should be using the diameter equivalent. Yeah, just be careful when you're dealing with the non-circular pipes. For example, for this one, somebody has already derived it. Just believe it. If not, then you can derive it by yourself. For this one, then the diameter equivalent will be this one. Or if you have pipe with rectangular cross-section area, like this one, with this size, and it's full like this, then the diameter equivalent will be this one. It will be different. Just remember, if it's not filled with the liquid or the pipe is not does not have the enclosure at the top, the formula of the diameter equivalent will be different. Okay, now if you are dealing with the non-circular pipes, the calculation of friction is actually need to be done into step manner. First, you need to calculate this one. This one is calculated by normal calculation. So you decided you calculate Reynolds number, but by using diameter equivalent, and then you uh, you decide first whether it's laminar or turbulent. Okay, then you can calculate FF. But you cannot use this one directly to calculate EF. You need to multiply it with the constant. This is called the non-circular constant or non-circular factor. This is specific based on the size and the cross-section of the pipe. So the one, FF, is using the equivalent diameters, this one, and then you multiply it by this one, then you will get this one, and this one you calculate by using the normal equation. How much is the value of the non-circular factor? It will be depending on the size and the cross-section of the geometry. So for example, if you have the cross-section of rectangular, then for laminar flow, you will have this equation. It will be the function of height and the width. For the turbulent flow, also function of the height and the width. This is you get the constant, the ratio. Don't forget, you still to calculate the equivalent diameters and then calculate the friction factor, then multiply this one and this one. For the annulus, the concentric annular shape, then for laminar, for turbulent, it has different equation. It will be function of the inner and outer diameter. So for the elliptical cross section, the diameter equivalent, you can use this equation, and then for the constant or the ratio, you can use this equation. Again, you do not need to memorize the equation. Just remember that you have to do 2 steps of calculation of friction factor of non-circular pipes. Calculate the friction factor based on Reynolds number first. Reynolds number is calculated using the equivalent diameter, and then you multiply with the non-circular constant or factor, the KNC. Then you get the final friction factor. You use the final friction factor into the formula of EF.
Sir, will KNC be given, sir?
KNC is given like this. You need to calculate as well. Like for the annular, this one, it will be depending on the value of the diameter, right? Because it has 2 diameters, the inside and outside diameters. Then the KNC can be calculated. But first, you need to decide the Reynolds number. Reynolds number is to decide the laminar or the turbulent. So the KNC will also the function of the Reynolds number.
So they will give the formula of KNC, right, sir?
Of course.
Okay, okay.
But either way, the exam is always in open book, right? Okay, any question after this one? Okay, if not, okay, how come the how come the latihan soal is not here? Can I show you the soal but in bahasa?
Yeah, sure, sir. Just Google Translate it for us, sir.
Okay, this one, just a minute. How come the soal is not there? Okay, this one. Okay, basically, I will translate directly, right? The natural gas. So natural gas is flowing from Sengkang to Parepare. We call it S2P. And then the flow rate of the well, because the natural gas is produced in the certain well, the flow rate of the well is 50 mm SCFD. This is the term that normally used oil and gas industry. So the flow rate is quantified with the unit of mmSCFD, million standard cubic feet per day. Okay, the length of the pipe is 70 kilometers. And then Sengkang is placed 300 meters higher than Parepare. So it means the inlet position will be higher than the outlet position. So Hs will be 300 plus H, sorry, not H, let's use this term Z for the okay, the gas has the molecular relative 17. The temperature of the gas is 30 degrees C, and the pressure will be in 60 kilogram per centimeter square. So this one should be kilogram force, because pressure will be force divided by area. Okay, you will have three types of pipe with 5, 10, and 15-inch diameter. All have the same roughness. The epsilon over D is 0.002. So P here is PS, right? Pressure at Sengkang, because the inlet pressure will be at Sengkang. So pressure at Sengkang is 60 kilogram force per square meters gauge. Please be careful, it's a gauge pressure. So you need to calculate how much is the outlet pressure. It means pressure at Parepare by using three size of diameter of pipe. Okay. I want you to do the calculation at home, and we will discuss it at our next class. But before I leave you to work on it, I need to explain a bit. So this one is mmSCFD. Million means 10 to the power of how much? Hello? Are you still with me?
Sorry, sir. Sorry, sir.
Million is 10 to the power of 6. Yes. Cubic feet per day. So to make to avoid error in your calculation, please do all the calculation in the standard unit. So you need to change it into, what is the standard unit of the flow rate? Cubic meters per second. Okay. But you need to understand that standard means the flow rate is calculated at certain pressure and temperature. Okay, can you check now? mmSCFD is calculated at which pressure and at which temperature? Can you check up online for me? How much is the pressure and how much is the temperature? Berapa? What will be the standard condition for MMSGFD calculation? Ada yang sudah dapat?
Kok nggak ada ya, Sir?
Ada.
Bentar, Sir. Pressure-nya 25 bars, bener nggak, Sir?
No, it's not that.
Sir, is it 50 bars, 80 degrees centigrade?
How much? How much?
Is it 50 bars?
No, no, not 50 bars. Standard
Yang 101 kilopascal sama 273 Kelvin, bener nggak, Sir?
berapa?
101 kilopascal
Mhm.
sama temperature-nya 273 Kelvin.
Try to convert 7273 Kelvin into Fahrenheit. How much?
To Fahrenheit. Oh my god, wait. Di sini dikasihnya 0 degree Celsius atau 273 Kelvin, Sir. Bentar ya.
0 degree Celsius is how much Fahrenheit?
Sir, is it 31.73 Fahrenheit?
30?
31.73?
No. Usually it's around 60. So the MMSCFD calculation is normally used at 60 Fahrenheit and around 180 M. I think it should be correct, the pressure one, but the temperature is around 60. Wait, why is different? Nol derajat Celcius itu berapa Fahrenheit sih? 32.
0 degree Celsius is 32, right, Sir? 32 Fahrenheit.
Okay, wait. If I'm not mistaken, it is calculated at around 60 degree Fahrenheit. Yep, one bar, 60 degree Fahrenheit. Okay, 60 degree Fahrenheit is how much Kelvin? The conversion from Fahrenheit to Kelvin.
Multiply by 9/5 plus 32, right, sir?
Yeah. So convert it to Celsius first, right? So it's around 288.7 Kelvin. Is that correct?
Yes, sir.
Yep. So MMSCFD is calculated at around 101 kPa, kilopascal, so around 100,000 Pascal, and 288.7 Kelvin. That's the condition to calculate the MMSCFD. But you know the actual condition, the pressure is 60 kilogram force per square centimeters, and the temperature is 30 degrees C. So what you need to do about that, you need to convert first from mmSCFD, you convert into cubic meters per second. But remember, that is in this condition, 180 M to 88.7 Kelvin. You need to convert into the flow rate, cubic meters per S, at 60 kilogram force per centimeter square gauge and 30 degrees C. How you do that? What kind of equation that we can use to convert the flow rate into the actual condition? Do you still remember? What is the equation that correlate pressure, temperature, and volume?
PV equals nRT, sir.
Yes, actually, it is called the equation of state, persamaan keadaan. The simplest equation of state is gas ideal equation. So PV equals nRT. Okay, for the certain amount of gas, when you change the pressure or you change the temperature, the moles will be the same, right? The mass of the gas or the mole of the gas will be the same. So basically, you can use the Boyle-Galussac equation. So at standard condition, 1 bar, 180 M, 288 Kelvin, the flow rate is this one, but you need to convert it first. Then at 60 and 30 degrees C, then you have the actual flow rate. Okay, understand?
Okay, sir.
Yeah, okay. So if you already know the actual flow rate in cubic meters per second, then what you need to do to calculate the pressure at, because you need to calculate the pressure at the outlet at pare-pare. You need to do the Bernoulli equation between point at Sengkang and point at pare-pare. It means you need to calculate the EF. EF is the function of friction factor, and friction factor is the function of the Reynolds number, and Reynolds number is the function of the diameter and what? Velocity.
Velocity.
So the velocity will be depending on the diameter of the pipe. For calculating the Reynolds number, you will need the value of density and viscosity, right?
Yes, sir.
How can you get the density? Do Do you still remember? You can use the gas ideal equation to calculate the density. Because you already know the pressure, the temperature. PV equals nRT, right? N is the mole. Mole is mass divided by N will be mass divided by
Divided by
molecular weight.
Yes.
Yeah, molecular weight. Mass divided by volume is density. Okay?
Yes, sir.
So you can get the value of the density. How about the viscosity?
Shear stressor.
No need. You know the gas has certain molecular weight. So please find out what type of the natural gas that have the molecular weight 17. Kira-kira apa?
Di atas oksigen 1, sir.
Di bawah dong.
Di bawah. Pusing,
What
sir.
is natural gas consist of? Do you know? What comprises
Natural gas
of
ada
natural gas?
C something something lah, sir.
Yeah, it's basically it's from C1 until certain C, right? So if it's only has the molecular weight of 17, so the close one is this one, right? The methane gas.
Yes, sir.
Methane gas is 16, of course, that is
16.
close, right? So please find out the viscosity of the methane gas at 30 degree C.
Boleh pakai Google, sir?
Boleh.
Oke.
Then later you can have the value of viscosity. Then you can calculate the Reynolds number. And then please calculate at home. Then we will discuss it at our next class. What is the result if you increase the diameter? How much is the pressure at the outlet of the pipe at pare-pare? Okay, any question? So that's all the step, right? I hope you already understand how to calculate. This is the types of our second exam. I get
Pertanyaannya cuma ada satu, sir, in our second exam.
sorry.
Pertanyaannya cuma ada
Of course,
satu, sir.
no. It's one of the question in the second exam. Because in the second exam, you will have pump and then you will have compressible fluid, right?
Okay, sir. Sir, another question, sir.
Yep.
For yang 5, 10, and 15 inches, the length nggak dikasih tahu ya, sir.
The
So there is no specific value of EF for 15, 10, and 5, ya, sir.
Yes, you can calculate. The length is 70 kilometers, right?
70 for each, ya, sir.
Yes, because the distance is 70 kilometers. So for each diameters, the length is the same, 70 kilometers. And the
Okay, sir.
already is also the same. So only the diameter is changing.
Okay, sir.
Okay, any question from others maybe?
Sir, I ada question lagi, sir.
Sure.
Yang fanning friction, yang friction factornya, katanya kan you can put it in a function of yang epsilon over D sama Reynolds number, sir.
Yep.
Yeah, that one how, like, what's actually the equation, sir? Like, cuman dikasih taunya kan you can put it in a function as of epsilon over D and Reynolds number, right, sir? Yeah.
Yeah. Basically, you can use two methods. First, use the empirical equation, but the empirical equations need to satisfy the requirement. For example, for this one, it's only for the smooth pipe. It means if the smooth pipe means this one is 0. Or if the Reynolds number is very, very high, the Reynolds number is very, very high, you can use this equation. But if it's in between, you can use this equation. But this equation requires you to do the circular calculation, the trial error equation. First, by guessing the friction and then get the second value, then put this one into this one and then do the iteration. Or the other methods is you are using this one. You calculate the Reynolds number. If it falls into the turbulent, you are using this graph. But you need to use the correct line. The correct line means the value of epsilon over d. Ini udah dijelaskan kan ya? Law or last discussion?
Udah sir.
Apa?
Cuman kayak banyak pisan inputnya sir, jadi pusing.
Okay, that's why if you can play again the recorded version of the lecture, and then if you still have question, you can ask me during the class. It's okay. But basically, for turbulent, you can use either this one, but this one, the general is this one. Actually, the graph comes from the Colebrook and White equation. But if it falls into this category or this category, you can use this equation. Oh, it's still in Indonesian because I opened the Indonesian slide. Okay. Or you can use this one. But if, for example, in our case, epsilon over d is berapa tadi? 0.002, right? 2 times 10 to the power of minus 3. This is 1 times 10 to the power of minus 3. And this one 6 times 10 to the power of minus 3. So 2 times 10 of the power of minus 3 should falls between these two lines. Then you can create another line between the 1 and 6.
Okay, sir.
Okay, so you calculate the Reynolds number, take the line upwards vertically, then crossing the line that you have already made, then take the line horizontally to the left, and then you can use the friction factor.
Okay, sir. Okay.
Previously, for the regular student, they found out the Reynolds number is very, very high. So they use this equation, can. If the Reynolds number is very, very high, means it already falls into the straight line over here. So the Reynolds number, the friction factor is already constant at that line. Then you can use the Nicordasa equation. Okay, any question? So please do the calculation by yourself first at home. But please be careful when converting the unit, okay? This one is already in absolute, mmSCFD, but the actual condition, the 60 kilogram force per square centimeters, is still in the gauge pressure. So you need to convert it to Pascal first. The pressure, the standard unit of pressure is Pascal. It's not kilopascal. Please be careful. It's Pascal, so you need to convert to Pascal. And then for the pressure at Sengkang, you need to put 100,132.5 Pascal to convert it into absolute pressure. Okay, that's all. Should be clear enough.
Yes, sir.
Okay, please do it at home. Do I need to translate it to the English before you can do it at home?
If it's possible, please do so, sir.
Yeah, okay.
So that we have a reference to look back, sir. Yeah.
Okay, then I will translate, and maybe later tonight or tomorrow I will send you the translated exercise. Okay, thank you very much for today. Then we will see you again next week. Good afternoon.
Thank you, Pak Wawan.
Thank you, sir.
Thank you, Pak Wawan.